Miriam did her PhD at Oxford. So first she did her bachelor studies at UNAM, at the Facultad de Ciencias. So then she did her PhD in Oxford. Then she did a first postdoc in Munich. Then he went to Bonn, and then he went to Heidelberg. And now she's a professor at the Institute of Physics in UNAM. And she's interested in astroparticles and also in physics beyond the standard model of physics particles. So she will talk us today about dark matter and beyond the standard model. So please, go ahead.
Thank you very much for the invitation. For some of you, I'm frequently here. So I think it's the first visit this year, but sometimes I'm more than once. So I'm going to talk about exploring dark matter beyond the standard model of particle physics. I'm going to cut short a bit my talk, but I have extra slides, so if you are interested in a particular topic, just let me know. So the outline is why go beyond the standard model, how to go beyond the standard model, or how I go beyond the standard model, some very brief overview of some of the still working candidates for dark matter, and then some challenges for all of us. So we are always thinking, what are we made of? And that's the same topic of worry for both astronomers, astrophysicists, and particle physicists, and probably more people. What is the origin of the universe, how it is evolving, what keeps everything holding together, what is everything made of? And from the particle physics point of view, the standard model and its extensions are our attempt to look at these things. It's probably, the standard model is not the last one, as we'll see, but it's a very working one. So why or how have we built this standard model? First of all, it's an interplay between theory and experiment. So sometimes the theory goes beyond, before the experiment. Sometimes the experiment finds something that the theoreticians have to think about, but basically it's an interplay between the two of them. And from the theoretical point of view, is based on symmetries. It's continuous symmetries, discrete symmetries, internal symmetries, gauge symmetries, broken symmetries, and we all know about them. For instance, continuous symmetries imply conserved quantities, like rotational symmetry implies the conservation of angular momentum. Translational symmetry implies momentum and energy conservation. Then we have, for instance, discrete symmetries like charge conjugation, parity, the specular transformation, or time reversal. And all these symmetries, Lorentz invariance, for instance, label and classify the particles. The internal symmetries are the symmetries that tell us what are the internal properties of a particle or group of particles. For instance, their spin, the different charges under the different interactions. And all of these symmetries, some of them are exact, some of them are badly broken, some of them are softly broken, some of them are spontaneously broken, some of these are called hidden symmetries, some of them looks like they're there and we don't know them, So for instance, for discrete symmetries, has, as I said, charge, parity, and time reversal, and we assume that the interactions are local, so localized in the point of science. There is not a small distance, but a point interaction, and that means that CPT, the three transformations, are conserved. So CPT in quantum field theory, as we see it in particle physics, is always conserved. P is violated, the parity, the transformation, in weak interactions, respected in electromagnetic interactions and in strong interactions. C, charge conjugation, is violated in weak interactions, and CP is violated in weak interactions, but not in strong interactions and electromagnetic ones. So just from these very simple three transformations, there is a kind of hodgepodge of how the particles behave. The standard model respects Poincare symmetry in 4 dimensions. The internal symmetries, as I said, are the ones that describe the properties of the particles. They're called gauge symmetries. For instance, SU3 as a gauge group for the strong interaction, and SU2 cross U1 for the electroweak interactions. Particles acquire mass through the Higgs mechanism, and this is absolutely fundamental, because if we put just a mass term in the Lagrangian, they would violate the gauge symmetries, and gauge symmetries are fundamental. It means that it doesn't matter how we describe a particle, the internal symmetries, the physics is the same. but we know that the Higgs mechanism works. The Higgs has been discovered, so previously the gauge bosons were discovered, so we were fairly sure that the Higgs was there. And we have two types of general particles: the fermions, which have half-integer spin, and the bosons, which have integer spin. And they have, as you know, very different statistics. And another odd thing about the Standard Model is that the only left-handed particles fill the electroweak symmetry. What left-handed particles, you decide the chirality of the particle as a projection of the spin direction of movement, and only the left-handed part, it has a combination, each particle of a left and right-handed part, and only they're all left-handed, they only, use the left part. So this is odd, yeah? And they have vastly different masses. So for being a fundamental theory, it's a bit strange, but it works incredibly well. And that you have to keep in mind. It works incredibly well. It works incredibly well, at least up to the energies we have been tested in the lab. So this is the Standard Model Lagrangian, written in a very compact notation. Is the gauge group is SU3 cross SU2 cross U1, as I said, strong, weak, and electromagnetic interactions, UKAW interactions mediated by the Higgs bosons, as those are the terms that are in the, I don't have a pointer, before in the third line. Oh, thank you. Okay. So that's, yeah, this acquires a vacuum expectation value, this is the Higgs field, and it all looks very nice. And this is our periodic table of elements, or the periodic, the Standard Model table. Fortunately, it's a lot simpler than the one from the chemist, so you can even memorize it just by looking at it. Perhaps not the masses. The masses are a bit tricky, but it's up, down, charm, straight, top, bottom. These have the same quantum numbers, have a fractional charge, which is odd, but it's there, 2/3 and -1/3. And then they come, these are the quarks, these are the leptons, these are confined inside the nucleus by the strong force. These are the gauge bosons, which carry the force or mediate the force. They're exchanging gauge bosons all the time, the particles, that's how they interact. The gluon, in principle, doesn't have a mass, but it has a color charge, which means that it can interact with all the quarks and with itself, so it gets a very, very complicated dynamics. So yesterday we had a fantastic introductions to quantum chromodynamics by Professor Daniel Burr in our institute, and now we have here the neutrinos, electron neutrino, electron, mu neutrino, muon, tau neutrino, tau. Again, fermions, this you all, well, electron everybody knows, neutrinos everybody has heard of, they're even in the news. And they have the photon, everybody has experience of the photon, gluon nobody, direct at least, but in the lab, yes. And the W and the W, which is charged, and the Z, which is neutral, which are gauge bosons. These are vector bosons, so they have spin 1. And then, of course, is the Higgs field. These electromagnetic and weak interactions, these are responsible for the decay of particles. These, you all know it, electromagnetic interactions. Quarks and leptons and gauge bosons field. The strong only the quarks. Yeah. And the gravity is not included in the Standard Model. So I put it here, it's very small in comparison to the strength of the other interactions. So it's there for some people who want to unify gravity with the rest, which is a very, very important thing to do, but we don't consider it here because it's the strength of gravitational interaction is much smaller than this, and the particle has very small mass compared to a planet, for instance. And we come to our first symmetry breaking. So spontaneous symmetry breaking is process, you start with a symmetry, but the state of minimal energy doesn't respect that symmetry. So there's a spontaneous symmetry breaking of our symmetry. For instance, we can have different types of breaking. So it's a phase transition, and for instance, you can start with something like water, and after a phase transition, you don't end up with ice, but you can end up with snow, for instance, with a completely different type of symmetry, yes, with appropriate conditions. But you can also have explicit symmetry breaking when you think like, this symmetry is almost there in my Lagrangian, but it's not quite CP variant, but I have a little bit, so I'll add a bit of term, I don't know where it comes from, so I can add a term in the Lagrangian which explicitly breaks that symmetry, and I see if it works for the purposes I want. But spontaneous symmetry breaking is associated to phase transitions, which, as you very well know, is what happened in the early universe. You know, starts the Big Bang and then it starts expanding and cooling down, and we have different phase transitions, and eventually we end up with our standard model. So that I'm not going to explain, because you know the Higgs potential is just going to say that it's the famous Mexican hat. We call it not the Mexican hat in Mexico, but because it's not a typical Mexican hat. It's a hat that was used by a small amount of people in a small amount of time in Mexico, but okay. So you are here in a perfect symmetry, but a local maximum. And then it falls down, whatever, we have a quantum fluctuation and falls this into this circle of minima, which they are, as you say, not exactly symmetric. They have different symmetry. There's a circular symmetry here. And that implies, oh, you can hardly see it here, the vacuum expectation value of the Higgs boson is different from zero. So our universe has a non-zero, let's say, that's permeated by Higgs bosons, and the vacuum expectation value of this Higgs boson that permeates our universe is not zero. So when something acquires mass, a particle basically, it borrows or takes some of this energy from the vacuum and gets on shell, which is what we call when it realizes as a particle. So this is the proportion, this is the vacuum expectation value of the W, of the big Higgs mass, this is the mass of the W boson, and this is how they couple to the Higgs. This is the gauge coupling, SU2 and U1. This is Higgs self-coupling, so the Higgs also acquires mass, and this is very good because then we could observe it experimentally. And this is how the fermions acquire mass. This is the Yukawa coupling, which is then the Higgs boson and the vacuum expectation value of the Higgs boson, and this is the Yukawa coupling. And if you remember our table, it turned out that we had a very nice table, and then I don't think you saw it, but the top quark has 172 approximately GeV of mass, but the up one has 10 to the 5 GeV smaller. So we're supposed to have two particles that are identical, but they interact with the Higgs boson, if we assume there is only one, very, very different. But a very different is not an order of 2, it's 10 to the 5, or almost 10 to the 6. So that's one of the first puzzles of the Standard Model. And this leads to another problem which has been puzzling us, and it still puzzles us, and we think that's why, I mean, among many other things, the Standard Model cannot be the ultimate theory. We think more or less it's going to be like one of the layers of an onion, and then we have another effective theory at some other higher energy and so on, or perhaps we have the desert and then we have an ultimate theory. But what we know is that, for instance, the Higgs mass is a scalar, has spin 0, and has different radiative corrections or type of radiative corrections to the other particles. Actually, they're quadratic. The other ones are logarithmic, and they tend to go like that with the energy, whereas quadratic go like that. So it means after some point, if we increase the energy, increase the radiative corrections and interaction of the Higgs mass with the vacuum, and we would have something like that. If we go all the way to the Planck scale, we would have the actual mass, which is by now measured 125.2 or something like that, around 125 GeV, and this would be the mass at the cutoff scale, which is the Planck scale, and the correction, yes? And if we want to, this is going to be the Planck scale, which is to 10 to the 19 GeV. If we want these two to cancel, we have to do something. Somebody actually calculated this number, and we have to have this number canceling this number in these two, I think it's something like 33 decimals to get to 125 GeV. Now, that is a fine-tuning problem. So if you think 10% is a fine-tuning problem, on 1/1% is a fine-tuning problem, no, our troubles are much bigger, yeah? And the other thing that tells us there is a problem is that of all the masses and couplings and the vacuum expectation value and how the particles mix with each other, these are free parameters in the Standard Model. What do I mean free parameters? It's not like I can put the mass of the electron to whatever I want. No, the mass is measured in the experiment, and the vacuum expectation value is measured in the experiment, the coupling, the strength of the coupling, but we cannot derive it from the Lagrangian. So that's what we mean by free parameters. We extract it from the experiment. So that's why the Standard Model has a very strong interplay, and whatever other theory, between experiment and theory. So here are the masses Yeah, so we have the electron, 0.5 MeV, the top quark, and the Higgs, which are similar in mass, 172, 125. And here we have the neutrinos, which we don't know actually what the masses. We know they're very, very light. We know the difference of the square masses, but at least there are another 5 orders of magnitude smaller than the electron. So we have a picture where our elementary particles span a really large range of values in masses. And our theory cannot tell us why. And all of them have been observed. And finally, there are many things like that in the Standard Model, but finally, I said the particles, only the left part interacts with the electroweak, feels the electroweak interaction. And that means that the particles are not, they are in a basis, which is the one that interacts, and a different basis, which is how we measure the mass. They're not in the same basis. So we have to use a transformation. It's just a matrix to change from one to the other. This is called the CKM matrix from the quarks, and the PMNS matrix for the neutrinos by the people who proposed it. So the quarks are almost, the mixing matrix is almost diagonal. So they have little mixing between the interacting states and the mass eigenstates. So it's very hierarchical. So we have this means that they can transform into each other, but the smaller these terms are, the less likely is that they'll decay or transform into each other. But with the neutrinos, they thought it was going to be the same, and it's not. It's very different, actually. So the PMNS is not hierarchical, yeah? So some of the terms here, the mixing is big, and here you have a column here, more or less the same size, and then this one is very small, so it looks a bit of a mess. Well, or at least not with a clear structure.
Excuse me, what do you have in mind by nu 1, nu 2, nu 3?
Those are the mass eigenstates. These are the interaction eigenstates, and these are the mass eigenstates. So they mix, yeah. So they're not. What they interact is not in the mass eigenstate. So you write the Lagrangian as interaction Lagrangian, and if you want to extract from that the particle masses, you have to change basis to the mass eigenstate. So you have to put a rotation matrix, yeah, and then you have a mixing between the interaction eigenstates and the mass eigenstates. Vice versa, if you for some reason write it in the mass eigenstate and you want to say how are they interacting, you have the mixture of the other states. In the quark case, it's almost hierarchical. It's almost like a unitary matrix, not quite, but these are almost of the order 1, not quite, as I said, but these are not. So it means that you have a large, the neutrinos are oscillating, yeah, and they thought they were going to be oscillating a little bit, but they turn out that they oscillate, the angles of oscillation are large, yeah? So they transform into each other. And this is counterintuitive if you want to think that they are like the quarks. Now, perhaps in retrospective, we shouldn't think that they are like the quarks because the quarks are confined and the electrons and the neutrinos or the leptons are not, yeah? But that was the idea. So in retrospective, perhaps it was not reasonable, but that is. And then on top of that, we have antimatter. Each particle has this antiparticle. And as you will know, what we get in the universe is what we call matter. And we have a little bit of antimatter that comes in cosmic rays or things from the cosmos, and we can produce it in the lab. But basically, we're made out of matter. But our Lagrangian tells us that we could have equal amount of antimatter if we wanted. Then it doesn't happen, yeah? And we wouldn't be in the universe we are now if it was the same amount, because it would have annihilated. So it's good that it happens, but we don't know. So now our table, if we unfold the table, it starts looking like that. Yeah, so we have the quarks in 3 different charges, which we call colors, because they always come in a neutral combination inside the nucleus. Or then the gluons, which have color and anticolor, there are 8. Then the gauge bosons, the Higgs, antileptons, antiquarks, and leptons. So it starts looking less elementary than we would like, which might be the way it is. Might be that we go up in higher energies and then we have a lot of particles. We don't know. We want the reductionist method, but it might be that is not the right way to go. So this is the back of the T-shirt, and where they expanded the Lagrangian to put this and all CP violation and lots of other features that we have observed. This works incredibly well at experimental level, but it starts looking a little more complicated, yes? So what part of it do you not understand? Well, so lots of parts of it we don't understand, so you cannot try to englobe everything, but I'm going to look at some of the things that are interesting to you. So the hierarchy problem, as I said, that's a theoretical pressing problem. Neutrino masses, why are they so tiny? Are they generated radiatively or through the seesaw mechanism, or what's going on with neutrinos? Origin of gauge interactions, that's again for the theoreticians. Dark matter. Dark matter is there. We have a lot of observational evidence, and we haven't been able to produce it or capture it, or well, capture its interactions. The baryogenesis of matter of antimatter abundance, the cosmological constant, and inflation. I'm not going to touch on these, but I'm going to concentrate on dark matter from the particle physics point of view. So this is the first proof that there is new physics, yeah? Again, the neutrino masses are proof that there is physics beyond the standard model, because the standard model was constructed to have massless neutrinos, yeah? And you can say, well, I just had another right-handed neutrino and a Yukawa interaction. Yes, you can do it, but you have to explain another 5 orders of magnitude between the electron and the heaviest neutrino. So yes, it's possible to do it, but it gets a bit odder, let's say, more odd. None of the standard model particles can account for 100% of that matter. Perhaps the neutrinos could be a small amount of the dark matter, but not all of them, yeah? Because if it were neutrinos, as you say, it would affect galaxy formation. So better explanation from the particle physics point of view requires new particles, yeah? So it happens everywhere, these dark matter halos, yes? They tend to be bigger than the normal visible, luminous, good, nice halos. Okay, so as I said, we have evidence of dark matter at different scales in the universe, the solar system, galaxies, clusters of galaxies, and in the observable universe. So Zwicky, as you know, looked at galaxy clusters. He was the one who proposed the term dark matter. He said, like, oh, it's more matter that it doesn't interact. Then Vera Ruby and Ford showed it in galaxies around the 60s. Then we have the bullet cluster and the temperature anisotropies, yeah? So there's a lot of evidence by now that we need more matter to explain it. So what do we know about dark matter from our point of view? It's electrically neutral, otherwise it would interact. It's non-baryonic, not made of protons or neutrons. It moved very slowly during formation of structures and has mean lifetime longer than the age of the universe. So it means it doesn't decay or decays very, very slowly. So it's the models prefer cold dark matter. This is the observed galaxy distribution, and hot dark matter, which we like neutrinos, yeah? So we're concentrating on, in particle physics, on cold or warm dark matter, yeah? And as we don't find anything, the models have become more and more complicated, or we have started thinking that our assumptions might be too simplistic, which is usually how you start to look for something, which is the easiest way. So what do we know of dark matter from the particle physics point of view? This is the page of the particle data group. You know, they don't print it unless you really ask for it anymore, because it's like this fat. But it's in the internet, so you go PDG particle physics, and you have all the properties and reviews of what we know about particles, decays, interactions. And this is what they have about dark matter. Mass, we don't know. Spin, we don't know. Mean lifetime, we don't know. It means it can be a boson, a vector boson, so a scalar, a vector boson, or a fermion, a Majorana fermion, a normal fermion. Decay modes, we don't know. So we're in the dark, literally. So now let's go to the particle physics point of view. We have the problem, many problems, so we know we have to go beyond the standard model. We're convinced for many years that we have to do it. The standard model, as I said, is one of the best tested theories experiments, especially the QED, the electrodynamics part, is really incredibly successful. So to go beyond it, you have to propose something new, and which doesn't spoil everything that has been measured. And that is a challenge, yes? So the most natural assumption is that we have the standard model here, and the rest of the new physics is somehow decoupled from it. Otherwise, we would have already seen some kind of radiative correction in masses and couplings and so on. So how do we go and how do we build a standard model? As I said, we add symmetries. These, or we add particles, or we add interactions. These three are interrelated. So we add the symmetries, it means we are adding as an interaction or a particle or both. Yeah. If we just add interaction, it usually implies another, say, gauge boson or another thing going on. So these three symmetries usually implies all these two. Then we add extra space dimensions, and you've all heard about string theory. I'm not going to talk about string theory, but I'm going to talk about Kaluza-Klein just mentioned, why are they interesting? And or we follow some fundamental principle. We are convinced that this is the right picture because of something. And or we follow some of the above, and many of the above are related, yeah? Follow some fundamental principle that implies that there's a larger symmetry group, and then all of the extra come. Now, the good thing, as we have a very, if you go to work in quantum field theory, is quantum field theories are well known. You can construct a quantum field theory if you propose a Lagrangian, and then you can make extrapolate at higher and lower energies with your computer, yeah, and then you can make predictions and see if your ansatz for a quantum field theory going with your standard model is correct, which is what we do all the time. So standard model extensions, some of them give good dark matter candidates. As I said, fermion, scalar, vectorial, you name it. And there is a vast mass range, yes? So it can be from the ultralight axion-like particles, which I think the lightest are 10 to the 23 electron volts, which are smaller, the mass is smaller than the limit on the mass of the photon. So I don't know how they're going to measure them. There you have a challenge, is that there are a lot of them, so that you hope that they form some kind of condensates, which could be observed. The more popular ones are not in 10 to the minus 23, but 10 to the minus 18 or something. Or it could be 10 to the 2 TeV if they are thermal relics. If they are not thermal relics, this can go way, way higher, yeah? And it's very difficult to detect. Where, as I said, well, you can produce them at colliders where you collide standard model particles, like at LHC, proton collisions, and then you can produce something, some dark matter particles, that's the hope. Or you can get indirect detection through thermal freeze-out, or indirect detection through collision with standard model particles, like here, something that comes from, say, an ultra-energetic gamma ray that hits something in the atmosphere, and then it's so energetic that produce, as a byproduct, a dark matter particle. You have less control of it, obviously, than when you have it in a collider. Or you can have direct detection, like an exam we went yesterday, when you put something that is very inert, like xenon or argon, and then you wait till the nucleus of dark matter collides with it. Okay, I'm going to go a bit faster. So these are the range of masses of dark particle masses. As I said, can be 10 to the minus 20-something GeV, so here. Then the axions of the standard model, which are 10 to the 9, 10 to the 10, something like that. WIMPs, which are widely studied, and we don't have to introduce another interaction. It's the weak interaction that is at work there, so we don't have to make more assumptions. Super winds like Gravitino, Kaluza-Klein, so they're even more weakly interactions. WIMPsila, the ones that would be non-thermal relics, 10 to the 12, 10 to the 15, or QUBO. So there's a large assortment of things that could be dark matter. Yeah.
I always get confused about one of those candidates are thermally.
The ones that are around WIMP are thermally produced. The ones that are very heavy and non-thermally produced. And of course, what I wanted to say is that you could have a mixture. Yeah? From the particle physics point of view, we could have one of each. Yeah, we can have a lot of them in the particle. From cosmology, no. Yeah, that would be the test, and that's the challenge. Yeah, we can construct theories where we can have a lot of things in there, and we probably have, but we're only looking at one sector of the theory, because I said it gets pretty complicated. But you can have more. Yeah, and that's, I think, the challenge there is to construct a model which doesn't violate any of the cosmological constraints, like Big Bang nucleosynthesis, galaxy formation, that gives you the right amount of dark matter relic density, and structure formation. Yes, and as far as I know, there are very crude models, but the people are starting to look at that. So supersymmetry has been one of our, in Spanish, caballito de batallas, or war horses, yeah? And it's still going to be looked for. So if you thought it was that, no, it's not there. It's just very fat, or very heavy, or very high energies, because it has one feature which for the theoreticians is important. With one assumption that you have a symmetry between bosons and fermions, which are the two fundamental types of particles, you can get rid of a lot of problems, which is the hierarchy problem. You can have good dark matter candidates, unification of fundamental forces, of quasi-unification. If we extrapolate the the couplings of the gauge couplings, we do see that they tend to a common value. If you add supersymmetry, they do meet, which is not a proof of existence, it's a proof of consistency. So it's consistent with many of our assumptions and the things we are observing. And it hasn't been found, unfortunately. It is a solution to the hierarchy problem. I give that a miss. And the other thing is that it doesn't violate any of the things that you have in the standard model if you assume that it's heavy and is decoupled with the other particles. And now this might seem like, okay, well, it's decoupled and so on. But all the other models, you have to decouple them by hand. Yeah. And here there are models which are naturally decoupled. Yeah. And those are the ones that have been are going to be investigated now. So this thing that I put here is compatible precision measurements of the standard model is not trivial. Many of our candidates have died there. Yeah. And it's consistent with thermal dark matter density. But as I said, they are remarkable coincidence, but might be just that. As you probably know, every SUSY particle comes with a standard model particle and a super partner. So suddenly our standard model looks a lot more complicated, or minimal SSM, minimal supersymmetric standard model needs at least 2 complex scalars, Higgs bosons, to give mass to all the particles without gauge anomalies. And on top of that, since I said we don't observe it, it has to be broken. In this case, we don't know a dynamical or a spontaneous breaking of symmetry. We assume it's at very high energies, but we have soft breaking terms, which we assume are the relic of a more fundamental mechanism that breaks supersymmetry. These are super renormalizable, so they would be natural there in the Lagrangian. Yeah, so it's from that point of view, they're well-behaved terms. Yeah, and different assumptions of how supersymmetry could be broken at very high energies lead to different predictions. But then the problem gets really odd because, ugly, very ugly, because we have over 100 extra parameters in our MSSM just to have this simple model and this simple picture. Yeah. So this thing, well, this is a very nice picture. This would be the MSSM, the minimal realistic version of the supersymmetric standard model. We have 2 charginos, 4 neutralinos. One of them is our dark matter candidate, and then we have the normal particles, and all the S quarks and gauginos and S leptons at high energies. And these are the Atlas SUSY searches, so they haven't found anything so far, and the mass scales start to be around TeVs. Now, what does it mean? It means that it's the hope that they will have, low energy supersymmetry is not there. And from the theoretical point of view, there are different these, like, it's unnatural and so on. But as I said, unnatural is the mass of the Higgs, where you have to go to the 33rd decimal to mix it. And we are only assuming this supersymmetry. This doesn't solve the thing of why are there 3 generations, or why are the masses of the normal particles so different, or why is there CP violation. So obviously, to try to cure that with only one assumption was a bit too optimistic, yes. We have to put extra assumptions if we want to understand baryogenesis, for instance, or the masses of the particles. But this is a very interesting slide. And I said SUSY has a natural decoupling limit. It has 5 Higgses, 2 scalars, normal scalars, 1 light, 1 heavy, naturally light, heavy, a pseudoscalar, and 2 charged ones. So if we found any Higgs that is not the standard model, that would be a hint for extended Higgs sectors or supersymmetry. Yeah? And this is a relatively recent analysis where they measure the W mass. Here is the W mass. So here's the actual standard model prediction. This is the experimental part, this oval here. This is where they hit each other. So the standard model is at the edge of this allowed part by the experiment. And this is the parameter space of one of the simplest SUSY models. So it fits better if you make an assumption of supersymmetry with a recent precision test of the standard model. Now, this I didn't know, so it's pretty surprising. It doesn't mean, again, that supersymmetry is there. It means that, again, adds a little bit of something to the standard model that makes it more compatible. But to understand, to go beyond the standard model, it's not enough. So the dark matter candidates can be the neutralino, which is a mixture, a mixed state of neutral particles. Could be the partner of the neutrino, the S neutrino, which would be the partner of the axion, the axinos. And the indirect detection is by missing energy. So you collide something here, and then you produce particles of the Standard Model, and then one of them goes into eventually neutralinos, which you detect as missing energy or as something similar, but say in the atmosphere. But there, of course, you don't have so much way of testing it. So we have, basically, they have of how these things interact, of how the neutralinos interact with the Standard Model particles and what type of neutralino they are. There are mixed states of the neutral particles, of the neutral partners. We can have a bulk region, focus point region, coagulation, or Higgs funnel. So they are neutralinos with different properties in the same model, depending on how the supersymmetry was broken. And that is very interesting, because if we could get something to distinguish between neutralinos, we measure something which looks like a neutralino with this type of SUSY breaking is going to behave as a neutralino different from neutralino with different type of SUSY breaking. So there is a connection with the fundamental physics, but we haven't found them. And the other thing is that this is how it will look. So here there are different, the constrained MSSM, which is the one that is very simplistic, oversimplified model perhaps, and that has been discarded, I would say, by now. But these are other versions of an MSSM with different assumptions of how SUSY or how the super partners are made. And you see that the regions of parameter space are very different, yeah? And some of them, like these ones, are out of reach of the current accelerators. So these could have indirect regions in the electroweak interactions or the Higgs decays or something like that. And this would be with the dark matter relic densities, the same type of different models. So here you would expect a very heavy LSP, a neutralino. They're only testing for neutralinos here with our parity intact. Our parity is a discrete symmetry. And as I said, different neutralinos have different characteristics. So what we did some years ago is look at the only electromagnetic form factor of a Majorana particle, that's its own antiparticle, like the neutralino. And what we found is that we can calculate the anapole moment. It turned out that it's actually measurable, and now it's been included in the searches, in the direct searches. They have a part which is the, electric dipole moment, monopole moment, and the anapole moment. Yeah, but if it's a Majorana particle, it could be a right-handed neutrino. Then what you would find, is that you could distinguish about different types of parameter space of different ways of SUSY breaking of the neutralino. So this is the allowed region. This is for low. The two Higgses of the MSSM are very little mixed, with the tangent beta as the ratio between the back expectation value of the two, almost excluded. But here, you would have all this region which is in the range of observation or detection, rather, of xenon 1 ton and lux and so on. So this is all the region where you could actually measure a neutralino in this very oversimplified mode. So because of this, now people are looking at this kind of electromagnetic form factors to characterize, if they find something, the neutralino. So we know that it's going to be very heavy because we haven't found anything in the accelerators. Other candidates, if you say that the R parity, this parity between super partners and normal particles is broken, it could be the gravitino. Another one could be the axino. The S neutrino is a bit too small, relic abundance. But one thing in all particle models, as I just said, is that it can be more than one. So it could be, a neutralino with an axino or axios or another Higgs, yeah? So let me go. Another, very quickly, to multi-Higgs models, you could have, as I said, in supersymmetry, you have more than two Higgses, but you could have them also without supersymmetry. These models without supersymmetry are more constrained than models with symmetry because they don't have a natural decoupling limit. Yeah, so you have to decouple them by hand. So a lot of the parameter space has been killed by the LHC searches. So I'm not going to go into the details of the Higgs models. I'm just going to say that in these Higgs models, what what is the dark matter candidates are inert Higgses. Inert Higgses means that they don't have a vacuum expectation value, so they don't give masses to the particles, and they have a discrete symmetry that it prevents them from decaying into standard model particles, or they can interact among each other. Yeah, so there are many types of inert Higgs doublet models, and they are without supersymmetry. Yeah.
Are they scalar?
They're scalar Higgses, yeah? And they have to be, you can have scalar Higgses charged, electrically charged. You can have them pseudoscalar, which are parity non-invariant, yeah? Or you can have them like the Higgs, which is CP invariant. And these are there. Some of them have been ruled out. So if you assume that the masses are almost degenerate, yes, this is what LEP would have excluded. And here is the exclusion limit. If you assume that they don't have the same masses, then you could still have heavy Higgses, which could be dark matter candidates in this region, like above, I would say, 500 GeV. Then they come the Kaluza-Klein theories. There can be Kaluza and Klein theorized that there might be a fifth dimension that is curled, a fifth space dimension that might be curled or compactified. They compactified it in a circle, and this is one of the motivations for string theory. So you start with a theory of Einstein gravity, but instead of 4 dimensions, 5 dimensions, one extra spacetime. And one of them is compactified in a very small circle, so we don't see it, yeah? But this, when you do the maths, which they have the spacetime, and this is a 5th dimension curled around itself, and it gives you an extra symmetry because it's curled around itself, which unifies the gauge and the gravity symmetries. And then you have an extra U1 gauge symmetry, which appears associated with the coordinate transformations on a circle. And the parameters of the two theories are connected because they have the same origin. So this is a very interesting thing. But from the particle physics point of view, not only the gravity point of view, this gives you a tower of massive scalars. So, and they have like in steps in mass. 0, 1n, 2n, divided by the compactification radius. So they have been looking for Kaluza-Klein particles at low energies, and they haven't found a massive tower of scalars. It's an infinite tower, so it would give a very clear signature in the experiments. But there are simplified models of this, not the Kaluza-Klein original theory is incompatible with our physics, but there are a bit more complicated models with more extra dimensions. We call universal extra dimensions. And they all have a Kaluza-Klein tower states, a Kaluza-Klein photon, a Kaluza-Klein Z boson, a Kaluza-Klein Higgs in non-minimal scenarios. You can make them supersymmetric or non-supersymmetric, but these can also give a good dark matter candidates. And this is also very interesting, yes? And how do we test these? Well, they have been trying to test them in the LHC, so there are limits because the compactification radius to be at the energies of the LHC would be very large, yes? And you would have observed them by now. So there are stringent limits about that. But they could come from being produced, for instance, with ultra-energetic, ultra-high energy cosmic rays or gamma ray bursts. Yes? So people are setting limits on what these massive Kaluza-Klein particles, which are dark matter candidates, could be. And this gives you, again, direct input on what the compactifications radii are in these simplified modes. So this is the green band here is the preferred 2 sigma W map region, yes? And this, again, is the mass of these particles, I don't know, as a KK photon, and the KK is set in 5 dimensions, yes? And here you have, again, they will be very, very massive, at the order of 1 or 2 TeVs, so out of the reach of the experiments. Now, as I said, and you know, neutrinos have masses, and what we assume is that they acquire through a seesaw, where the right-handed part is very heavy, and the left-handed part is light, and we have a Majorana part too, and they mix, and then eventually we have something like very light neutrinos as we observe. The other way they could acquire masses is radiatively, for instance, by interacting with other particles, for instance, with supersymmetric particles in our parity violation. The coupling between those two would be very small. They are non-thermally produced, the right-handed neutrinos. They're mixing angles, so they don't mix a lot with does not reach thermal equilibrium, near thermal, and they produce warm dark matter. And again, there's a wide range of masses for the right-handed neutrinos, but only the ones that are in the range of keV can be dark matter candidates. But we could have right-handed neutrinos anyway for other purposes of our theory, like for explaining the small masses of the left-handed neutrinos we observe, yes? So this is the KeV neutrinos, which is a good candidate to dark matter, and the very light ones are not, as we know. The GeV, no, are not candidates for dark matter, and also all the way to very, very high energies. So these are also tried to be tested, and here are the right-hand neutrinos as dark matter limits in this point. And they look for decay lines in X-rays. This is the mixing, the mass and the mixing interaction strength, the mixing angle of the interaction. And finally, I'm just going to mention axions, which I said are ultralight particles. Axions come naturally in the standard model because, as I said, CP is broken in electroweak interactions like decays, but not in the strong. And in principle, if you just write the Lagrangian like that, you would have a really bad or very strong CP violation with the quarks. And it's not observed. Actually, it's very, very, very small. Otherwise, we will have an electron dipole moment. And this is tiny. So Peche and Quinn thought, okay, perhaps the term that in the Lagrangian that it accounts for this strong breaking of CP is not just a term like that, but it's a field. So they promoted this term to a field, and they said it corresponds to U1 symmetry, which is broken, and it gives a pseudoscalar. So CP non-invariant. And this cures very well the CP strong problem and produces, because it's a broken symmetry, a particle, which is the axion, which has a very small mass and a very weak interaction, so it's practically undetectable. It was practically undetectable a few years ago, but it's been trying to be detected now. You can have also an axino. So it's a possible candidate for dark matter because, again, it doesn't decay, interacts very weakly. But these two, which ranges of masses, which would be natural for the standard model axion, have been excluded. So there's a small window for the axion in the standard model, but it's still there. And it couldn't be anymore because of astrophysical constraints. I think I'm not sure if it's gamma ray bursts or something, not in this mass range. But when string theories had a lot of axion-like candidates, which I was talking about at the beginning of the talk, which could be from 10 to the minus 33 to 10 to the minus 80 electron volts. Now, axions, because they are bosons, they form conglomerates. They have a different statistic than fermions, and they could leave an imprint in astrophysics, which is caustics. Caustics are these things that when you see at the bottom of the swimming pool how the light rays form, and you have these rings. So CKV, which is the one who proposed it, realized that if they're a lot and they're light and they could agglutinate, they would leave some kind of structure imprint in the galaxies or clusters of galaxies. So they're looking for that right now. I don't know how they are or if they were there, how the dynamics of the galaxies would destroy these caustics or how strong they would be. So again, from the particle point of view, if I have, let's say, a supersymmetric model, I would have an axion. Otherwise, I would have to worry about the strong CPP problem. And then I would have an axino. So they would be there anyway. Yeah. The same could be said for multi-Higgs models without supersymmetry. Now, we have masses for the neutrinos I had mentioned, because a normal MSSM would have to have right-handed neutrinos, axions, axinos, S neutrinos, and all of them mixed. There are many possibilities, and very few people have looked at just like MSSM, but with everything in there, and say more than one dark matter particle, or even at a non-supersymmetric model. They're just starting, and as I said, the challenge we are ingenious, so we can just put symmetries and things like that to make 3 dark matter candidates, but the problem is going to come from cosmology, galaxy formation, and Big Bang nucleosynthesis. And the models we have, which are built either at high or low energy, have to meet at some point in our searches, yeah? I'm going to put this one, because we have a very, very difficult challenge for particle physics and astroparticle physics in the detection of dark matter. And one of them is all the uncertainty factors that come here. So this is indirect detection with Hawk of, say, Kaluza-Klein particles or heavy scalars or whatever, or neutralinos or heavy neutralinos. We have here an astrophysical, this is the flux that is measured by Hawk, let's say, gamma ray. And this is the astrophysical factor, and this is the particle physics part. So the astrophysical factor assumes a lot of things, and if you actually put the exclusion plots with the limits, the bands are really big, because we don't know exactly, and you know much better than I do about this, what is the density, we are assuming a lot of things of the escape velocity, of the profiles, and the local density here in our nearby. And if we are observing something far away, like in Hawk, whether there's a clump of dark matter in the middle that is distorting things or not. But also from the particle physics part, we're always assuming 100% of the dark matter is neutralinos. And we have never really checked all the possibilities, or, well, some people have checked and they're starting to do it now, yeah. But the models are too simplistic from both points of view, yes. But here we have a very good control if we do direct detection, more or less. If we do collider physics, yes. If we do indirect detection, like cosmic rays or gamma ray burst, it's the uncertainties are bigger. And if we add here the astrophysical factor, what I learned yesterday at an exam, is that if you add them as statistical, as systematical errors, then your exclusion plots go up, yeah, even if you're controlling a lot the particle physics part, yeah, or the detector part. So we really need a lot of input for the astrophysicist to know how to take into account these things, and models that are a bit more complicated than what we are doing so far, yeah? Because we keep on finding more and more indirect, well, not direct evidence of dark matter, but it's there, indirect evidence. So many dark matter candidates, which are WIMPs and non-WIMPs, and probably if we go and see how our standard model particle data, well, table is probably more than one. Somebody said, oh, but it's more difficult. Yeah, but it would be odd that all the dark part of the universe was accounted for one type of particle. Even the Higgs sector is probably more than one. Because if you unfold all the possibilities of quarks, you have a lot of, they have 3 different colors each type. That means 3 times 6, 18, plus the antiparticles, 36, yes? So, okay. Heavy candidates are natural, and also very light candidates are natural, and intermediate candidates are, in not so simplistic models, still valid. And different perspectives and advantages for each of these candidates, but probably it's a mix of these, which means that for the halo formation makes a more complicated problem, yes, because you have different particles with different masses and different WIMPs, let's say, they would interact differently. So the challenges for both astrophysics and the particle physics part is to look for models which solve several problems with fewer assumptions, yes? So we don't have more and more free parameters. Neutralinos could be, they're heavy, but depends strongly on the model assumption, which is something that nobody tells you when they're showing the plots. All the information in the plots of the LHC, ATLAS, EMS is done in very simplified models. As I showed, if you go to more complicated models, use parameter space change. They can say, okay, this is typical of this, in general, of SUSY, so they can discard regions of parameter space because they don't see signals. But different models are going to produce different parameter spaces. Models with multipartite dark matter are now available, a few, but we necessary to build realistic ones. And by that, I mean that we look more at the cosmology and the astrophysics part. And we need a combination of astroparticle physics, cosmology, direct searches, indirect searches, and more realistic halo models, and the uncertainty is better determined. So it's a lot of work for all of us. Thank you.
Questions for Miriam? So I have a comment.
Yeah.
So, well, it's interesting. It seems that having a dark matter particle candidate is very natural, comes very natural within the standard model, because extensions to the standard model. Yeah, that's right. So, because I heard some people saying that it's weird to have dark matter particles within the nature, and it's more natural to just modify gravity and all that. But it seems that we have a lot of candidates that
there are a lot of candidates. Almost there are lots of extensions. There are good extensions that solve other problems like supersymmetry or multi-Higgs models or right-handed neutrinos. All of them have very good solid theoretical basis, and all of them provide good dark matter candidates.
That's right. So and now the problem is become which one is the,
Which one, how your model, have to be sort of not too complicated, specific Baroque models, but more generic models, but they have more than one. Say a multi-Higgs model that have a scalar, inert scalar that can be plus a right-handed neutrino. That is very natural. That comes in a lot of models. Now the thing is, okay, put both of them as dark matter candidates. They're very nice, and then go and calculate weight density and all the things. Yeah.
And depending on the particle, it will be the range of masses that you need to look.
That's right.
From the point of view of cosmic structure formation and also from recent observations, apparently there are some more requests for dark matter particle candidates.
Yeah.
For example, self-interaction. So
Yes,
from
right.
those that you mentioned, SUSY particles, for example, can have some
Yes,
self-interaction.
they have self-interactions, neutralino, neutralinos, other neutralinos estados, so they have a lot of interaction. Higgses have naturally self-interactions and interactions. You can have a dark sector with more Higgses, and they will have interactions among themselves, for instance, yes.
Okay.
Right now, let's say simplistic models have been analyzed, but there people are starting to look at more complicated models. Yes, they would have self-interactions, and they could have annihilation in different channels, depends on the interactions. Perhaps you have lines here and other lines here from other of the particles, If you have more than one candidate, you can have a lot more things that you think like, okay, this is not compatible with my assumption. Yes, because you're assuming that it's 100% of this type, but if you use 30, 50, and then something else, then
And the other thing is that with observations, recently this H 21 centimeter line,
right.
the H experiment showed that probably it's necessary that the dark matter have some ability to interact with standard model particles.
That's right.
The millicharge or something
That's
like
right.
that. So there are some
yes, all of these
proposal for that.
all of these are weakly interacting. See, so all of these have interactions, but not tree levels or not, but at radiative corrections with standard model particles. And how small or big is interaction depends not only on the strength of interaction, but on the mass of the particle. Yeah, because in the vertex you have the mass and the strength. And for instance, in neutralino models, it is specific to the type of breaking or the type of soft breaking terms you have. So that's nice. Yeah, and you could have more. As I said, in the NSSM, they always tell you the LSP, but you have also an axiom unless you have something else that it occurs to you to solve the strong CP problem that everybody's happy with the axiom. So your extension of the standard model, although you don't say it, has an axiom there. Otherwise, you have a really big problem on the CP strong QCD sector. And if it's supersymmetric, it has an axino. Yeah. So okay, if you have a multi-Higgs, no SUSY, you still have an axiom, because otherwise, again, you have the strong CP problem. But they never tell you, yes? And very few people look at all of these transversally, say, oh, I had this symmetry, and I'm going to look at all these sectors because it's very complicated. I'm not a QCD expert, so if I wanted to look at that, I would have to pair with some people that are QCD experts and say, like, okay, if I have this explicitly, this term, how would it affect your part? Which means for more collaborations, and it's
Thank you.
positive.
Okay, well, let's thank Miriam again.
Thank you.
And so we have some snacks, and we will come back at 1:30 for the small presentations for the students. And the students that are, I will change to Spanish. Los estudiantes que van a hacer sus presentaciones, por favor, quédense para ver el orden y todo esto. But the other people, please go to the lunch. For the snacks.